There we go. Okay, it's 1 o'clock. I've started the recording for those that are going to be watching this on YouTube later, in case they couldn't make it, because I know there's the AP meeting. We're going to end this. I'm going to try and end this around 1:30, 1:40, just to make sure that the information gets to you, but also so that those that have AP classes and need to go to that meeting don't get bogged down or can get anything they need to get done before the 2 o'clock meeting. So I will have chat open. If you have any questions, you can message me in there, or if you just want to speak out with the mic, go right ahead. We're going to actually be learning about refractions today, which, as you can see on the screen, hopefully is displaying, is a different old white guy in a in a pool. It's not me, but that is also a way of seeing how this effect occurs, the bending of light as it goes through mediums. I'm going to give everyone another 2 minutes to log in or so, and then we're going to move on. All right, well, we only have a few here, but I got messages from other people that are saying they're not going to make it today because they had one-on-ones with teachers or for other reasons. That's fine. That's why this is recorded. So we're going to talk about refraction, and you guys hopefully watch the video on Brain Genie. That should give you most of the information, at least in the most mathematical sense. It told you what was happening, but not really why or the reasoning and all that stuff. But it really has to do with, well, this severed head man in the picture. If you notice, you can tell quite easily that his body is obviously over here and his head is over here, and that's not right, and it shouldn't be that way. The reason why is because as light is traveling in through this sheet of glass and the water, it causes it to bend. It's like when you run on a different surface. If you run on cement, it's really easy to run. Your feet can grip very nicely and push forward and move, and it's perfectly fine. But if you're running on sand, it gets, it gives and it slows you down, and it's harder to move. Trying to run through really thick, deep mud, you're basically not running anymore. You're just kind of like trunching through, just big steps. That's just like with light. Light can travel through space very fast, but it can't travel through things like glass and water as fast. It's still really fast, but it's not the same speed as it was if it was a vacuum. And that's what happens. It slows down a bit, causing it to bend. And you see this in basically everyday life whenever you deal with any kind of liquid. In fact, this is a famous picture online, but there's also one that was on Life magazine. This was taken in the 1950s. So you can see that the swimmer, obviously the head's connected to the body. It's ridiculous to not think so. But because the light traveling underwater distorts its direction a bit, we get this effect going on where it looks like the body and the head are in two different places. In fact, what you see, I do a little cruddy drawing of this, is if I have a pool, and let's make it blue water. Ooh, fancy. And I put down there, got someone coming in. There we go. Okay, and I want to, let's see, put a little coin at the bottom. I'm going to put a little coin right there. It's all shiny. And me and my, I think I selected the black, there it goes. Me and my eyeball. This is my eyeball. I don't know why my pupil's suddenly coming out of my head, but it is. It sees that coin. Well, the light that's bouncing off this coin, that's going to go into my head. I keep getting more people coming in. That light that's coming off of this coin. Anyone who's coming in late, if you need to catch the beginning, or if you have any questions, message in the chat. But this will also be up on YouTube to rewatch. But this coin, light is going to come off of it and into my eye. Any other object, like, I don't know, a balloon, light's going to come off of it, go into my eye, and that light will be in a straight line. Light doesn't like going in at weird angles unless it has to. So it's going to go in the straightest possible line. But this coin, it's going to go up towards the light, or up towards the water here, and then bend towards my eye. This bend right here is what you were calculating before, these two different angles. Now, my eye sees the coin, but since it thinks the light's going in a straight line, it actually thinks the coin is over here. It's in the wrong place. That's what that distortional break on the person is. And you see this too if you ever deal with like water. Here, I'm going to go to full screen on my camera. Hi. So, like, I got a big old glass of water for this demonstration. You can see the water, nice, cold, and crisp, and can I get the? Great for a hot day like today, isn't this? Ah, yeah. But if I take a straw, something very visibly red, and I insert it, I'm going to make sure it's at the right level. Got to angle it a bit because the camera. You can notice that there is a very slight break right there. It's not a huge break because there's not a ton of water. The further I go back, the more it shows. You can see that break. That's because the light that's coming out of the glass is actually coming at a different angle and bending towards you, so your eyes follow it back to where you think it is. And your brain goes, oh, light travels in a straight direction. Why should I not believe otherwise? And it makes the image. That's how you see it. So that's kind of the effect of refraction. And we're going to go over the exact definitions and the equations and all that stuff right now. But before I move on, are there any questions on the concept of light bending? It's a magic straw. I get it. Yes, I understand. I know that I, in my wizardry powers, allow for magic, like this. See, it's all bent now. But like this straw is just a straight line. And you can even do it with your finger. Oop. Welcome back. Like you can even do it with your finger or any other object. You can even see like it magnifies it a bit, which we'll cover a little later. But like, especially if I do it at an angle, you can notice that it doesn't quite stay straight with my finger. It bends it a little bit. But you can see that when everyone's in a pool or underwater. In fact, we even see it with light and the stars and the sky and everything. When the sun sets, you can see different colors. And the reason why is because refraction bends light depending upon its, well, technically about its frequency and such, but you can actually cause the light to bend more. Things like blue light bend very, very easily. It's a very small wavelength. Think of it as a little tiny thing, and it gets knocked around by air molecules really easily. That's why we see blue up in the sky, but when it gets to sunset, we see red, because red has much longer wavelengths, so it can burst through the atmosphere and it doesn't affect us, or it doesn't get scattered away. In fact, when you see the sun going over the horizon, it's actually a little bit further than you think it is, because the light's getting bent around the surface of the planet, and it's coming in, and you're seeing just a little bit farther of the horizon and such. It's a neat little effect. But let's get over some of the details so you can see the the equation and the math behind it and the definitions, because next week we're going to be doing a Snell's Law lab. It's an interactive lab through PhET. I'll have a video up that shows you how to set up and take the data. It's going to be a fill-in-the-blank form, and it's a really good way to kind of show you how this all works. Next week, and remember, I'm trying to stretch these things out because you have your science fair paper coming up. Don't forget about that. But we're going to talk about lenses and your eyeballs and how these things work, and how there is literally a hole right there that you see into, and how eyes and cameras work, which is a lot of fun. All right, so let's get to the presentation real quick. And just get over to there we go. Okay, I'm going to share just the small part of the screen, so that way you can see what I'm doing, and I can also see the chat still if you need to message me. All right, so refraction, lenses, and sight. So this is refraction. This is the definition of refraction. Refraction is the change in direction of a wave. Now, waves can be sound or light. Yes, you can bend sound. If you guys ever remember in the hallway, there was those pictures of all the teachers from when they were in college. There's a picture of me on there if you ever go back to look at it. And it's me standing in front of my bachelor's degree science project for my degree. It was a sound telescope. I bent sound to focus into a single spot. So it can change any wave. So if you refract a wave, it means you're bending it. And it can be sound wave, surface wave, light wave, earthquake, whatever. The refraction, the bending, occurs whenever it crosses from some medium to another medium that the wave travels at different speeds in. Different things will travel at different speeds in different mediums. Light travels faster when there's less matter in there. And sound kind of does the opposite. The denser the material is, the faster sound travels. Your voice underwater, when you speak and you hear, the reason why it sounds so low-pitched, lower frequency, is because the wavelength is getting bigger. The wave is traveling out of your mouth faster than you're used to. So the wave stretches, so the frequency goes down. That means, like underwater, you actually make sound that travels faster than if you were in air. And that distortion can occur, the bending can occur, it goes between air and water. So we have here our incident ray. This is our vocabulary terms that were in the video from before, so I'm not going to spend a lot of time on them, but incident ray means the ray of light coming in. The angle of incidence is the angle that light ray makes with the surface. The boundary is, well, the border between the two surfaces. The angle of refraction and refracted ray are the ray that's inside the second material. Now, whether material 1 or material 2 is whatever object, you decide. You can flip it around, make it go other directions. That doesn't matter. If I sent a beam of light going up this way and it hit the surface at the same angle, it would pop out at the same angle. It reverses. So don't freak out if you're like, I don't know which one's the medium one. Always has to be air. Yeah, it doesn't always have to be. Sometimes it's water, sometimes it's glass, sometimes it's a diamond and quartz or whatever. It doesn't really matter. All right, this is the equation for the index of refraction. That n value right here, which I'm going to. It's not going to let me select the pen. Well, I think part of my computer is frozen. Am I still broadcasting, I hope? Well, I've got a weird little pop-up going up on my screen. I don't know if you can see me still. Give me a second. Let me stop presenting for half a second. Okay, I still see myself on the broadcast. All right, that was weird. Oh, well. I guess I won't be able to draw on as much as I wanted. put it back on. Presentation. Okay, so that should be back up. All right, law of index of refraction. I'll just type it in here. This top part, this speed right here, that speed of light in vacuum is known as the speed of light. It's 300 million meters per second, or 3.0 times 10 to the 8th meters per second. You don't have to memorize it. I'll be putting it in other things. But this is also referred to as, wait, did my screen just crash? Nope, it's still there. Okay, that's referred to as c, the speed of light. In the shirt that I've been wearing today, I have my You Matter shirt, if you can see in the little screen. But that You Matter shirt that I talk about, where it has the You Matter unless you multiply yourselves by the speed of light squared, that's E equals mc squared. The c in that equation is the same c in this equation. It's the speed of light. You don't have to memorize the number. If you ever need it, you can look it up. It's not a problem. But just so you know, the speed of light is really freaking fast. The speed of light in material, it's going to be less. It's not going to go as fast as in space. In space, there's nothing stopping it. It is the openest road you can get. It can go full speed and nothing's going to stop it. But once it gets to atmosphere or glass, it's going to slow down. It's got to push its way through. It's got to go out of my way. You know, it's like going through a crowded room. So if you ever want to know what the index of refraction is, you take the speed of light in the vacuum. Well, is it now letting me draw? Well, so this is C. I don't know why it's a highlighter, but it is. And that equals 3 times 10 to the 8th meters per second. Wow. Can I get, oh, I might be able to get the pen. Hold on. Let's erase that. I guess it's somehow caught up. So this is C, and that is equal to 3 times 10 to the 8th meters per second. Oh, is the screen frozen? I was having some issues, so like I'm worried about that. I don't know if you guys can hear me. Okay, you guys can hear me? Can you see what I was writing on there? Oh, you know what? Let's do this. Give me a second. I think I know why. It's probably a layering thing. Hold on, I can fix that. Let's just, are you your own index of refraction? Well, you have an index, you have more than one index of refraction. Let's just do this. Entire window presentation. Okay, whole screen's up. This way I can see the chat, and yeah, I'm on the index of refraction slide. Do you not see it? I mean, I just did a new presentation through the whole screen. Okay, so let's just back up a second to make sure everyone's clear on this. So this right here, this speed of light in a vacuum, that is known as C. C is 3 times 10 to the 8th meters per second. I got it. Once someone's trying to go in. No, that's not what I wanted. Okay, so this is known as the speed of light. This is how fast something can travel in space. It's the fastest anything can travel. When you hear the speed of light, people think of that as like the fastest and like light can travel. Well, actually, it's the fastest any information can travel. We can't go faster than this. It isn't that light goes this speed. It's that nothing can go faster than this, and light goes as fast as it possibly can. There are other things that also go as fast, like neutrinos and other electromagnetic spectrum things, but we call it the speed of light because that was how we first calculated it. Right. The speed of light in the material could be any velocity. It's just velocity, some number, whatever, meters per second. Now notice, if I have meters per second divided by meters per second, they will both cancel out. N has no units. It's just like the friction coefficient, if you remember that. Remember we talked about friction coefficient like last semester? I know it's way back there in your head, and you're like, I don't remember this. I don't know this. Well, we had this number called the coefficient of friction. If you guys remember, friction is fun. It's that number right there. The mu, that coefficient of friction means how rough a surface is. The higher the number, the rougher it was. It never really got above 1, but you get like a coefficient of 0.6, which means like 60% roughness. Like it's pretty rough. Ice would be like 0.001 roughness, so it's super smooth. Same thing with this. This doesn't have units because it's a relationship of these two numbers. It generally has a number above 1. The reason why is because if you ever get a number below 1, think about that for a second in math. That means that the bottom had to be bigger than the top, and the top is the biggest number and the fastest anything can travel. If you get a decimal for an index value, please let us know, because you have discovered something faster than the speed of light, and we want to use that. All right, before I move on, because we had all the jumping around and the freezing, is there any questions before I move on? There's only like a few slides. This isn't a very long presentation. Yeah. Not seeing any comments saying that you can't see anything, so I'm going to move on to the next slide. Gotta do that. Okay, Snell's law. There you go. So Snell's law, you've already calculated in. We have our index angle of incidence, the index ray. We got the refracted ray. We've got this. This we've seen before. N1 sine theta 1 equals N2 sine theta 2. From the people who've already asked me questions, and from what I've seen from the homework so far, it doesn't look like there's a ton of questions, but from the people who tried it, there's quite a few that haven't finished it yet or tried it. Is there any part of this equation that you need me to go over? Because there is the video on Play Pause It that goes over how to calculate with this equation. Okay. I mean, it's not a super difficult equation. It's fairly linear. The hardest part is finding your theta when you say you have to take that inverse sign on the calculator. Just make sure that it's the sign with a -1 on the top. Otherwise, you could get incorrect answers and things like that. So just make sure you go through carefully. But yeah, it's a very simple calculation. But this is actually how lenses work. This is how your eyeball works. This is how vision works underwater, inside gases, whatever. So it's a very nice system to understand that the angles are going to bend the same for everything. It's also how mirages are made. And one of our favorite things, oh, sorry, here's a list of some index of refractions. You see that even a vacuum has 1. That's the lowest index of refraction you can get. And then they can get up pretty high. And the higher it gets, the slower the light went, the more it bent. If you ever have a decimal number, you went way too far in one direction. But this dispersion, this is the other thing that can happen. Rainbows! Rainbows are great, aren't they? They're pretty, they're fun, they look up in the sky. You can create them with a sprinkler and a little bit of lighting and some pre-planned. I'm going to show you how to make, or I'm going to teach you how to make rainbows in your yard, which today during a sunny hot day might not be a bad idea. So dispersion is on the base word disperse, to spread out, to send out. So if you tell a crowd to disperse, you're telling them to move away from each other and spread out, social distancing kind of thing. Oh, you know the album? Good. Dark Side of the Moon. Yeah. Yeah, they made this very famous, even though it's been around for. This is actually Isaac Newton's originally. Like he's the one that came up with that concept drawing and such. because he's the one that figured out how that white light is based up of primary colors, like a set of colors that actually spread out from the singular white light. So this white light comes in, hits the boundary at a certain angle, causing it to spread. Oh, Newton had an ego bigger than his hair, like that. But it causes it to spread out, and then it hits another boundary, which causes it to bend a little bit more. And that bending is a little more severe. The bending happens right here and right here. And what happens is it gets a little more severe. It's a little bit more for the shorter wavelengths. It's basically, when you're in a large crowd, the smaller, skinnier, not so big, bigger kids are going to be pushed around a bit more. The blue wavelength is super high energy, small child. It gets pushed a little more. It can sneak through a lot easier, but it's going to get kind of pushed in a way, and it can't really fight against it. So when the blue wave hits the glass, it gets bent more. The red wave is like your big football player. He's just going to kind of go through. He gets bent a little bit just to try and navigate, but doesn't get pushed as much. So this is how rainbows are made. Well, not quite. Rainbows aren't made exactly like this. There aren't triangular shapes of water flying from the sky that bend the light. What there are instead are raindrops. So rainbows come in, or light comes in at a rainbow, and it's a sphere, and it bounces off the back, and then bends again. And it's very particular. It's got to be this 42-degree angle. Like, don't worry about actually calculating it, like figuring all that stuff out, but it has to be a specific angle. That's why they're not always around. And the light source always has to be coming in from behind. So if you were here, so let's say this was you were standing over here. Move myself over a bit more. Let's move this up so that I can actually see it. Notice the light source has to be coming in from behind you. So if you ever want to see a rainbow on a sunny day, you need to have the light coming in from behind you, probably lower in the sky than, say, noon, but it's still possible. And then spray a spray of water, like with a mister, or take your hose with a thumb line, spray it up in front of you. You will see a rainbow because the light will come in from behind you, hit the water in front of you, bounce in the water, and then send it flying back out to you. And you'll be able to see a rainbow. And pour back. So that's the basics of what refraction is. It's just bending of light. Now don't worry about figuring out the angle based upon the wavelength color. There will be a little bit of that in the next the lab thing, but for all the calculations, we're just assuming the very simple version of Snell's law where we don't have to worry about the wavelengths, because the bending isn't severe. It's just when you bend, reflect, and then bend again. So refraction, reflection, refraction, it starts adding up. It's like tax isn't that big of a deal. It's only like 10%. I mean, it's still annoying, but it really doesn't super hit you hard until you start spending a lot of money at once. Then all of a sudden you're like, dang, why am I spending 50 extra bucks? Oh, it's because I spent $500 and therefore tax is 50 bucks. Well, not quite, but yeah, that kind of thing. That number didn't work out, but that's okay. All right, so that's pretty much the entire thing. Lenses are what we're going to do next week, but there's a pretty rainbow for you. So just to make sure, if you want, I can do more questions or more examples or the same stuff that you did in your homework if you want. Other than that, I wanted to end this meeting around now, so about 1:30, and leave it only for people who need help, because you do have a 2 p.m. AP meeting. And I want to make sure that if you want to get some work done because you just figured something out, you get to get it done, or anything along those lines. So if you have any more questions, just let me know. I'll stick around for the next little bit. Oh, I play with this thinking. Look, it's a wave. There's a half a wave. Oops, it's hard to do this from up high. There we go. 2 waves, or 1 full wave. And how come a yo-yo comes back? Ooh, actually, that's a great question, and it has to do with conservation of momentum and rotational momentum. Simple version. Roll of tape, right? Now, unlike tape, the yo-yo string can actually roll around it. But as the yo-yo rolls down, it's still got this rotating momentum. Now, the string is loose and lets the yo-yo rotate around it. But the way the string loops on, the way you tie a yo-yo, you pull on it and it catches the spinning motion. Now it's got a hold of it. It's put friction on it. Now it still wants to keep moving. So now, as I was rolling it down, I have a string here. Power cord, this will work. So this acts kind of looks like a string. As it's rolling down this string, it gets to the bottom and it's still got this rotational motion. Then I pull on the string, it locks the string, it grabs it, it goes to the other side of the string, and now if you'll notice the way it was rolling, this is rolling up. So it rolls itself back up. Yeah, it's because it goes from one side of the string, where on this side of the string, it's rolling down, and then it goes down to the bottom of it. And notice it's still rotating the same way that it was before. And then it goes on this side of the string, and that rotation makes it go up the string. Not quite what we were doing. That's more first semester kind of Newton stuff, but basically it's the conservation of momentum. For those that are still here, here's the one unit you barely got by. Here's another fun little fact with slinkies. Let's see if I can get this far enough away. I can get this to stop. An interesting thing about the slinky is that the bottom, because of Newton's laws, this ring on the very, very bottom is being held up by the ring above it, and that ring is being held by the ring above it, and so on and so forth, all the way up to here. The tension, remember that from Newton's laws and Newton's free body diagrams, the tension is facing up on this very bottom ring, which means that when I let go of this top part, it doesn't fall like this. It falls by collapsing the top part down because it's still holding it up as it falls. I'm trying to show you, although it's a smaller slinky, but especially if you happen to have like video or something, you can see even faster. I just gotta wait till it stabilizes. So I'm gonna let go of it, and you'll notice that it will collapse before this bottom part starts falling. Pretty fast, I'll do it again. So there's the bottom. So I don't know how easily you can see that, but that's kind of a fun thing about the way slinkies work. All right. Okay, good. I mean, I could try, you know what? Since I'm not gonna have my earplug plugged in, let me try this. Let me try a big one. I gotta stand way back here. And I can't use the whole slinky because this thing stretches the entire length of my room. All right, hopefully I don't jam this thing up. It should be right at the base of the slinky. All right, so I'm gonna let go. Yeah, it's too big. The top part falls faster than the rest. I'm ready for a big boom. Yeah, this one works a lot better for showing it, just because I can get a little bit closer to the camera. All right, but it looks like most of the people have left. So I hope you all are doing well and you're keeping safe and you're, keeping cool, especially during this heat. Remember, I am here every morning from 9 to 11, just sitting at my computer waiting for people to ask me for help on Remind. So please don't be afraid to chat with me if you need it. And I hope you guys are doing well. If you have any questions on your science fair, please email me. Please talk to me. Just communicate. I'm here. And I hope to see you guys at least next year in the hallways. So take care.